Here's a programming challenge that I like to call condense. So, the idea of this challenge is you take a random sequence of numbers, and what we want to do is we want to condense it so that anytime any two numbers appear together, they basically condense and fizzle out. So if you ever see any two numbers that are identical and next to each other, remove them from the sequence and continue processing the sequence. So if we look over here, this sequence right here is an interesting candidate. Let's see what we have here. So we have we've got 1, 3, 9, 3, 1, 9, 3, 1, 7, 7, 9. Well, maybe this isn't the best example. Well, in this example, we're only looking for numbers that are directly next to each other. And so in this example, these 7s match each other. And so these should be removed from the sequence, and it should leave it just like that. But here, let me just make up another sequence. What if we had something like 5, 4, 3, 2, 2, 3, 4, 6. Well, if you had a sequence like this, what should happen is you should process through it, and if you ever saw something like these 2s together, the 2s match, so they should cancel each other out. But now that they've canceled each other out, that means that these 3s are next to each other. So when you actually cancel something out, you do need to make sure that you're not making two other identical things squeeze next to each other. So really these 3s should cancel each other out, and then that means that these 4s are going to cancel each other out. So the total correct answer for this one is just going to return the sequence 5, 6. So the challenge to you is to take this code. You have a function called a random sequence, which I made the random sequence go up to 100 here. It makes an array, and it just chooses random numbers between 1 and 10 and pushes them on that array. And your job is to write this function called condense to go through that sequence and just keep condensing it until everything is exactly the same. And just for the sake of us all being on the same page, I'm going to paste in this sequence that I generated, so you'll have access to that. There you go. Good luck. Okay, now that you've had a chance to attempt this yourself, let's work together to figure out a way to solve it. So one thing to notice about this is you can solve this problem with arrays or with strings. For instance, one way to solve this problem is you could make a for loop, and you could go through the let's just write this in one way with a string solution. So one way we could do this is we could say let's let the result be equal to an empty string, and we could say let I equal 0, I is less than the sequence dot length, and I goes up, and we could say let C1 equals sequence dot char at I, and C2 is I plus 1. And now we could say if C1 does not equal C2, result plus equals C1. So this just means that we're moving through the string, looking at two things at a time, and we're only going to append the last item if the two things were not a match. In fact, let's work on a simpler sequence for now. Let's use the sequence I set up above: 5, 4, 3, 2, 2, 3, 4, 6. So if we use this for loop approach where we're building a string, it's going to look at the 5 and the 4, and it will append the 5. It's going to look at the 4 and the 3. It's going to append the 4. It's going to look at the 3 and the 2. It will append the 3. Now it's going to look at the 2 and the 2, and it will not append that first 2. And then it's going to, if we leave the for loop as it is, it's going to compare the 2 and the 3, and it would append that 2. But we actually need a way for this thing to, we should get rid of that second 2 as well. So really, if they are the same, we should actually increment I again, just to make sure that I skips over that other index that we want to condense away. So now it's going to look at the 3 and the 4, and if that doesn't work, then, or if they don't match, then the 3 will be appended. It's going to compare the 4 and the 6. The 4 will be appended. We do have a boundary problem where we're at the end of the array, and the 6 might compare itself to something off the end of the array. So we should really be careful with the bounds of this for loop and stop it before it reaches the end. But I think what we can do is at the end, maybe we can have another thing at the end that says if the sequence, if the character at the sequence length minus 2 does not equal the sequence, the character at the length minus 1, well, maybe then we could append that last character. And this should be parentheses, not brackets. So this is a good start, but it doesn't account for I think what this would do, we should return result at the end of this. It doesn't do a good job of catching the first 2's that are together, but this method does not actually do a good job of catching those 3's which will become put together. So if we run this, let's just see how it runs right now. Yeah, so it catches the 2's, but it doesn't do a good job of going back when the 3's are together after that. So if we really want this thing to work, I think what we need to do is we need to scan over that whole string again in order to do this over and over again until really nothing does condense. We could, well, let's try this. So what we can do is we can do this. We can surround the whole thing in a while loop. And we can say while is unchanged. So we can give ourselves a variable here that says that this thing is considered unchanged. Or how about a different name? How about did condense happen? I'm trying to get something about something that we can just a Boolean value that will indicate that that we had a change. Yeah, you know what? I think is unchanged is fine. So how about is unchanged starts as true. I think we actually want the opposite of this. How about while it's dirty? We'll say it starts as dirty, and we'll say while this is dirty, it should process it. And if any of these things ever are dirty, that is to say, if there's ever a match where it was condensed, we'll say this thing was dirty. And at the beginning of each of these loops, we can say, assume this will be a clean, unchanged iteration with no condenses until we see two numbers next to each other that are a match. So we're going to say that I'm going to add a comment up here that says, assume we need to go through, assume the sequence is dirty to begin with and requires at least one iteration to check for numbers next to each other that should be condensed. So we use this Boolean value and we say, well, we assume that something is dirty, and then when we get into the while loop, we say, well, actually we assume it's clean, we check for everything, and if we ever see anything next to each other that did need to be condensed, then we say, well, we're going to need to, this thing is now considered dirty because we're going to need to loop through it again to check again to see if there's any more things after these two have been squished and condensed out to see if there's anything else left. And at the end of each of these, I think we want to update the sequence. I'm going to change the name of result to maybe next sequence. So now we're appending the numbers to the next sequence, and once we go through the whole thing, we update the sequence to be the new one, which is condensed, but with this while loop, it might take us several iterations to go through it. So let's see how this works. So this totally is correct. I mean, it works. But it's definitely not the most efficient way to go through it. In fact, let's time it and see how long it takes for a sequence that is long. And let's do this. Let's try and time it for one that's even longer. I'm going to say let sequence equals random sequence of 10,000. This random sequence returns us a array. I'm going to join that array so that this thing actually returns a string. Well, that was pretty quick. Let's try it with 100,000. Let's try it with 1,000,000. Okay, so with 1,000,000, we finally see it take a second. It takes 0.756 seconds. Let's actually try it at 1, 2, 3, 1, 2, 3. Let's try it at 10 million. So even the difference between 1 million and 10 million, we can see that this approach actually takes a long time. So there, we can see that at 1 million, that took it about 0.756 seconds, and at 10 million, this says it took it 12.36 seconds. So the problem with this version of condense is that, well, it's inefficient. It passes through the sequence of the string, and it actually requires moving through that sequence again and again and again and again. So let's try and solve this using a stack and see if we can get this to perform faster. So let's start off. I've copied this file, so now we're going to create an efficient version of this, and I'm going to rename this function Inefficient-Condense. So now let's write one that is more efficient. I'm just going to call it condense again. There we've got our sequence. Before we really do that, I want to program this with just the simple sequence of 5, 4, 3, 2, 2, 3, 4, 6, because we just need a simple case to try these things out. So the first thing that we should do with our sequence is let's make our sequence become a stack. In JavaScript, we can do that by splitting the string by an empty string, and that's going to convert it to an array. And in JavaScript, we're lucky that the array has the push and pop operations, which are the only things we're going to use, and that will make it stack-like. So convert the sequence of numbers into a stack-like array. And we're also going to make a stack, which we're going to make just an array, but we're also going to populate it with one thing from the sequence. Create a second stack and add one thing from the sequence to this stack. So the idea that we're going to do here is instead, so in the last one we had the string and we had to keep going over it and over it and over it again. What we're going to do for this is we're going to have two different stacks. It's going to look like this. We're going to have stack 1 right here and stack 2 over here. And right now, stack 2 just is starting with, we've taken the number 6 and put it over here. So the initial stack just looks like 5, 4, 3, 2, 2, 3, 4. Sorry, this is stuff I wrote before. And what we're going to do is we're going to pop two things off of these stacks. So we're going to, we put one thing over here just so we can pop something off. So here, we're going to pop off from stack 1 and see what that looks like. And we're going to pop something off of stack 2. And since both of these don't match, we're going to push both of those things back onto this stack. So 6 is pushed back on, and 4 will be pushed back on here, and 4 is not here anymore. And then we're going to pop off these elements from the stack again. So now we're comparing 3 to 4, and those don't match, so now we can push both of those back onto this stack. And 3 is out of that stack. Now we're going to pop off the top two things again. We're going to compare 2 to 3. Those do not match, so they should not be condensed. So 2 will go over here, and this 2 is gone. Now this is where the condensing actually happens. When we pop off these two elements again, we're now comparing a 2 and a 2. And since those are a match, what we do is we simply do not put them back on the stack. Now we're going to compare the 3 and the 3. So these each get popped off. Since they're a match, they do not get pushed back on. We continue popping off each thing from the stack. So we have the 4 and the 4. Those match, so they're not pushed back on. Finally, we're going to compare the 5 and the 6. And since those do not match, we push them back in. So the 6 goes back in, and now the 5 is actually inside there as well. And it's done over here. And we know we're done when we don't have anything left in the left stack. So the general idea is we have two stacks. We will put a single thing in the right stack at first, and then our algorithm is as long as there's things in the left stack, we're going to pop from every stack, from each stack. We're going to compare the two pairs next to each other, and if they do not match, we'll push them over here, and if they do match, we will simply not put them back into either stack. So let's write that. We'll say, wow, the sequence, the length of this one is greater than 0. We want to pop things off each stack. I'm going to say let left equal sequence.pop and right equal stack.pop. And we can say if the left thing does not equal the right thing, then what we want to do is we want to push both of those into the right stack. So we want to say stack.push. First we want to push the thing that came off itself, and then we push the thing that was from the left. So notice here, I'm being careful to maintain the order of this, where when we compared the 4 and the 6, the 4 came from the left and the 6 came from the right. So we make sure to push the thing that came from the right back down first, so that when we push the next thing, it stays on top of it and it maintains the proper order. So, let's see what happens here. We are going through the entire sequence. And let's, at the very end, let's try and return the stack. And let's go ahead and join it back as a string. I don't want to do code, I want to do node. This is just complaining that I used the word let for sequence, so let's delete that. Sequence is already defined as a parameter. There we go. So this is nearly correct, but it's backwards. So remember that when I've put things in here, if you pop everything out of one stack and push it into another stack, one side effect of that is that it's actually going to be reversed. So before we return all this stuff, let's unreverse it. And we're going to do that by saying, while this stack has anything in it, we're going to take the original sequence and push everything by popping it one by one off the other stack. So, one by one off the new stack, back onto the first stack to undo the reversed order. So that's just one property of stacks. In fact, let me draw that out just to make that clear. So if you have a stack of numbers here, so if we have the numbers 1, 2, 3, 4, 5, and if we started in the beginning and we were iterating this way and we pushed them in, we would push them in like 1, 2, 3, 4, 5 by pushing them in. But if we popped them out after that, well, when we popped them out, we would get the sequence 5, 4, 3, 2, 1. Because this is actually a last in, first out data structure. So we say this is a LIFO, which is last in, first out. This is like grocery stores when you have a milk carton and you load them from the back. So, actually, no, that's incorrect. So the way that we can get this back to its original order is we can take each of these numbers and we can put them back in a stack. So now we can do 5, 4, 3, 2, 1. And when we pop each of those out, now it's going to come back out as 1, 2, 3, 4, 5. So I just want to take a moment to talk about that, because that's just something that's common with stacks. When you put something in and then you pop it all out, it's going to come back out in a reverse order. So all we're doing here is we are doing that exact process of taking everything that we put in the second stack and we're popping it and we're putting it back in this stack, and that's going to unreverse it. And now I am returning the wrong stack, so we have an empty string here. We don't want to return stack.join, we want to return the sequence. So that works. Great. So now let's see, we have shown that this works for a small string. Let's see how it works for a really large string. So I'm going to make a string which is 10 million in size. Well, let's try the 1 million first. So even here, we're already seeing a efficiency gain. For a string of 1 million, it's at 0.28 seconds. So let's add the comments here. Inefficient while for string solution took efficient stack solution for 1 million took 0.28 seconds. Now let's see how it'll do for 10 million. That only took 2.3 seconds. So one thing we can see here is the stack solution actually has a factor of about 10x. So when we went from 1 million to 10 million, we can see that the time it took went up by about a factor of 10. And that's because the stack solution has a big O of n. We know that the pop and the push methods are a constant time operation. So no matter how long the array is, it's just going to take the same amount of time to read something from the end of the array or write something back to the end of the array. And we're only doing it for the length of the sequence. And even though we're doing that twice, this is the old 2n. So we only really iterate through the sequence about once here. And we have to iterate it through it again here to unreverse it, but that 2n simplifies down to just n. Whereas here, the inefficient condense, we have to build up a string the whole time, and we have this for loop, which has to go through the entire string. But the worst case scenario is we might have to do this while loop and go through that entire string again and again and again and again. So this is actually an n squared solution. So when we went from 1 million to 10 million, whereas we might expect this to look like something like 7 seconds, it actually went up to 12 seconds. And I bet if we did the inefficient condense and we went up to, let's try and do it. Let's just go up to 20 million and see how much that does. Inefficient condense. Well, let's do the 20 million for the efficient one first. Should take about 5 seconds. And I did not update the 2 over here. 1, 2, 3, 4, 5. So 4.80 seconds. But now let's try it for the inefficient condense, and I think it's going to take longer than 25 seconds. In fact, we might as well get a stopwatch. And let's see, I'll be surprised if it occurs in less than 25 seconds. Because that algorithm is not an O of n, which means it's not going to scale proportionally to the size of the input. I think it's going to be bigger than that. We'll see if it finishes in even under a minute. Well, it printed something out. My computer's really freaking out. I'm gonna have to stop this. Well, anyways, that took much longer, as you can see.